dear, a female deer, ray, a drop of golden sun. Me, my name, I call myself, far, a long, long way to run. Still, a pulling thread, love, a note to follow suit. Tea, I drink with jam and bread, that will bring us back to do, do, re, mi, fa, sol, la, ti, do.
Hey, I want to play the piano.
Now?
Yeah?
But where will we get the piano from? And what song do you want to play?
We could sing Do Re Mi.
I know you like it.
We could use a DAC.
Oh yes, we have the DAC, and with the lab view we can create our own piano.
Yes, and that way we can play it anywhere and anytime.
Perfect, let's do it.
Yes. Hi, I'm Sreya,
Hi, I'm Abhishek.
and we are doing the piano keyboard.
For our Embedded Systems EE4455 project.
To implement our piano keyboard, we used a data acquisition device from National Instruments called MyDAC. MyDAC is used to do the signal processing, and we connect it to the USB port of our computer, and the audio in of the MyDAC is connected to our PC output. The audio out of the MyDAC, which will be the process signal, is connected to our speakers.
Let's now look at the graphical user interface that we have designed. On the left hand side of the GUI, we have all the graphs that help us visualize the different signals being played on the piano. On the top, we have the amplitude versus time graph, which shows how amplitude of the signal changes with time as we play the piano. The middle graph represents the power spectral density of the signal, which basically describes how the power of the piano signal being played is distributed over different frequencies. And the lowermost graph depicts how amplitude and frequency of the signal interact with each other. Let's now move on to the right side of the GUI. In the middle, we have the piano interface that we will be playing. It shows only one octave here, from C of one octave to C of the next higher octave, with D, E, F, G, A and B in between.
On the top, we can use the sliders to vary the amplitudes or gain values of the different harmonics, or more precisely in piano lingo, the overtones. We have made provision for the first, third and fifth overtones with varying amplitude selections along with the fundamental frequency. On the bottom part, we can increase or decrease the volume using the slider. Instead of implementing only 3 octaves as required in the project, all 7 octaves of the piano can be selected and played by changing the octave number using the knob. Another additional feature comes from this file name interface, where a user can select any text file to store the values of the piano keys that he or she is playing, thus helping to go through the keys of any song he or she played at a later time.
Now we will give you a live demonstration. Let's run the program. So now if we press the key of the piano, we will see the fundamental frequency of the middle octave, fourth octave being played, and we can visualize that in the graphs here. So we can see that the frequency lies in the range of 300 to 500. Now if we change the octave to a higher octave, say octave 7, we can see that the frequencies will shift to a higher range of about 2000, 2500 till 4000 Hertz. And if we reduce the octave to a smaller octave, say 2, we can see that the frequencies will reduce to a very low value of C, only about 100 or even less than that.
We will now look at the harmonics and amplitude control. Let us set the octave back to a middle octave at 4. Let us change the amplitude of the first harmonic, and on the top graph you will notice that 2 signals are being shown of the 2 harmonics. In the second graph, you will notice that two different frequencies are being shown of the which show the power of the frequencies that are being played. Now I will increase the amplitude of the third and fifth harmonics, and on the graphs you will notice multiple frequencies, and on the amplitude graph you will notice that there are multiple sine waves. Let me change the amplitudes once again. Over here you can notice how the power of the different frequencies are changing.
The third graph below is the amplitude versus frequency graph. Here we can see there's some low frequency channel noise which is of very low amplitude, and thus we can't see it in this power graph because its power is very low. Now let's talk about the volume. Directly from the graphical user interface we can increase or decrease the volume. If we increase the volume to approximately 100%, we will see that the amplitude is very high, and if we decrease this volume to a low level, we will see that the amplitude also decreases. Now let me talk about an additional feature that we have implemented. So any composer who is composing his music, he doesn't need to worry about writing down his notes as he's composing. LabVIEW will automatically save all his notes. So on the interface, this file name helps the user to save it in a text file. The user goes and selects a text file and names it in the extension of .lvm. So now the user can play anything and it will get recorded. Now all these notes from C, D, E, F, G, A, B, C must have been recorded in the text file. Let's have a look at it.
This is the file that we have saved and which the composer can open later to check his notes. On the left we see the time, and the second column we see the notes. This is the conversion table for the notes. When there is -1, it means no notes are being played. For 0, it means C has been played. 2 would mean D has been played. And we see that 4, 7, 9 would mean E, G and A have been played.
We will now go through the block diagram for the piano. On the left, we have an array storing integers for all the 13 musical notes. When a note is played on the piano, then the array returns the corresponding integer. This integer is used to retrieve the frequency of the musical note from notes array. The notes are entered in this array in the same sequence as the keys are laid out on the keyboard. Then a sine wave of that frequency is generated, and it is sent to the audio out. The sound is then played through the loudspeakers of the laptop. The array returns a value of -1 when no key is pressed, which does not have a corresponding frequency in the notes array, and hence no sound is heard.
We will now look at the save to file feature. We use the write to measurement file component to save the integer returned by the array. The output of the array goes to the signal property of the measurement file. This component selects the output file, and the data is saved dynamically as we are playing the piano. Next, we will look at the octaves. To implement the 7 octaves, we scale the frequencies up or down. The notes array contains frequencies of the 4th octave. To get frequencies of the 5th octave, we multiply it by 2. For the 6th octave, we multiply by 2 to the power of 2, and so on. This is easier to do in an embedded system because multiplying by a power of 2 is just a binary shift. The knob on the front screen returns the value of the octave selected by the user. We will now go into the sub-VI of the octaves. This value is then subtracted from 4 and we raise it to the power of 2 and scale the frequency. For example, if the value selected by the user is 7, then the subtractor performs 7 minus 4, which is equal to 3. We have another component which does 2 to the power of n. That means 2 to the power of 3, which is equal to 8. And the frequency is scaled by a factor of 8.
Next, we are going to talk about the harmonics. We have added the first, third and fifth harmonics. To implement the harmonics, we have created a sub-VI, which looks like this. The frequency of the first harmonic is twice the fundamental frequency. The third is 4 times the fundamental frequency, and the fifth is 6 times. In addition, we can also scale the amplitude as chosen by the user for each harmonic. Additional sine waves are now generated, and the piano sounds much more melodious with the additional overtones.
After adding the harmonics to the signal, there is an added functionality of stopping the data acquisition. The volume level selected by the user is multiplied by the overall signal, thus increasing or decreasing the amplitude. Next, in the last part, we have displayed 3 types of waveforms, which can be seen in the front panel. First is the amplitude versus the time waveform. That same signal is processed through this block to show the power spectrum density of different frequencies. In the third waveform, we do the fast Fourier transform and display the amplitude versus frequency graph.
Now, we have implemented the piano using LabVIEW and MyDAC. And now we can play the piano anywhere and anytime we want. So, let's sing. Do, a dear,